Talk will be Professor Udayan Darji. He is from the University of Louisville, and he will talk about local entropy and applications. Please.
Thanks, Alfred. So, you look at the camera, right? Okay. Now you gotta be like, make me self-conscious. Think about how I look and not the math. No, okay. So I'd like to thank Alfred and the department here for having me here for a couple of weeks. So this talk is about dynamics, but not linear dynamics. And so about 10 years ago or so, maybe a little bit longer, I got interested in what's called local entropy theory. And so I realized, hey, this has a lot of potential, right? So I was able to exploit local entropy theory in like different areas, 3 different areas. And so I'll only talk about one different area here today. And so the idea is, so instead of going into lots of details, because we have 35 minutes, so I'll just give you more of the general idea of what local entropy theory is and how it's being used and so forth. So let's get started. So entropy, right? So what's entropy? Here we go. Entropy is a measure of disorder and chaos in a system, whatever all those things mean, right? So there are lots of ways of defining chaos and so on, but very loosely speaking, okay, we have this. And so the origin is in thermodynamics by Clausius in 1800s, long time ago, right? And then we have statistical mechanics by Boltzmann and Gibbs and Planck, and then quantum mechanics by von Neumann, and now we're getting closer to sort of information theory by Shannon. To me, this entropy here, it actually intuitively makes, for me personally, makes a lot of sense. And so if you want to hear about this sometime, I mean, after the talk or the next few days that I'm here, I can tell you why the entropy is defined in the way it is, for intuitively speaking. And the way Shannon did it is by you have information going through zeros and ones, and you want to compress it. That's and so for example, okay, I'll give you a quick idea without losing time here. But suppose I have a coin, heads or so let's say probably 0 or 1. Okay. Suppose it's got 1 on both sides. I flip it a million times, and I want to send you that information. Okay, so I can say 1, 1, 1, 1, 1, 1, 1, 1, 1 million times. That's not very efficient. I can say I'm sending you 1 million times. Very efficient. Do you see what I mean? We have some sort of code. So it's very easy. If it's all always 1, it's easy to however many millions I have. I said, okay, I just write down million is 2 to the 10th or something like this, approximately, right? Or 2 to the 20th. Yeah, 2 to the. I forget, probably 2 to the 10th or something like this. Okay. So I can just send you. That information is very small amount of information. But now suppose that the same coin, probability of 1 is 0.9 and probability of 0 is 0.1. I flip it a million times. Okay? But now, I know about 90% of them are 1s and 10% are 0. But I don't know which one goes where. Okay? So if I do it without thinking, I just said, okay, I send you 1, 0, 1, in the obvious way. Okay? So that I have to send you a million strings of symbols. Okay, but the point here is Shannon said, like, look, you could do this much better. And how fast could you? So you can compress this information in a smart way. And if you actually work it out, some ideas from real analysis stuff, you get the exact formula for entropy that you see in dynamical systems or Gaudic theory and so on. Okay, so that's the reason this is like one of my. So this gives you sort of an idea about. Why is it like p log p, right? Why not, p squared log p? Why not whatever formula you want? Okay? So if you're interested in hearing about this sometime, I can tell you more detail. It's like 10, 15 minutes. Okay. The dynamical systems, there's the same definition. This was a measure theoretic dynamical system. This was defined by Kolmogorov-Sinai. So this is like basically a discrete. You got a die, and you flip it, and you get that. Now when you generalize this to measure theory. Same idea, but then you develop the theory. This is Kolmogorov-Sinai measure theoretic dynamics, and then in topological dynamics, you have Adler, Kuhnheim, McAndrews. They define it there. And then Bowen and Dinberg give you this metric definition that you see in dynamical systems. Okay, so what's local entropy theory? So this is over 20 years, is a culmination of deep results in dynamics, ergodic theory, and combinatorics. So this involves really interesting combinatorics in there. So basically it does the following. Given a dynamical system with positive entropy, it gives in some sense the location of where the entropy resides. Okay, I'll make this a little bit more precise later. Moreover, it gives combinatorial tools which can be used to study the location of entropy. Again, this is very loosely, but I'll state more precisely later. So this started with the seminal work of Blanchard in the 90s, and then lots of, okay, I didn't write down the name of everybody, lots of people, Glassner, Wise, holding up, lots of people, okay, did a bunch of work, but then at the end, culmination of sort of like everything, put together and then some more stuff by Kerr Lee. So they gave actually a unified approach to local entropy theory. Okay, so this was in late 2000, 2009, 2010 or something like this. And a good survey paper is by Glassner and E. So there where you find all the reference for work done by lots of other people. And this is an ETDS in 2009. So let's get started. Okay, so this is sort of, so what applications, what have I been able to do? So, okay, so when I learned this, I like to learn new things that I don't know anything about, right? And then I learned it, I'm like, wow, this has a lot of power. I should be able to exploit it, right? And so I was visiting in Japan, this Japanese mathematician, Isao Kato. And so there's some problems in topological dynamics, but this involves more topology, right? And this is a thing that I'll talk about in detail. So if you have a positive entropy, it implies indecomposability in the domain, right? In the state space. And so this was something. So there was a partial result dating back to the 80s, and the general question was still open. And the problem was that. So suppose I give you a function, okay, even on an interval, and I said, hey, it has positive entropy. How do you use it? If I just give you an abstract function, it's got positive entropy. We'll define entropy in a second. Okay? So on the interval, you have some nice theorems like Sharkowski's theorem and classical theorems that says positive entropy is the same thing as having a periodic point not a power of 2 and so on. So you can exploit it. But in general, that doesn't work. So things that were known were on the interval, the general questions were open, and we were able to settle that. And then with Nielsen and Vermeersch, so a completely different direction. So you start with a topological dynamical system. For example, X is a compact metric space, T is continuous. Then you look at all the measures, probability measures on X. Okay, and then you say, hey, okay, got that, that's a new space. And then this thing, you just look at the T, gives you, in the image, it gives you a new measure, push forward measure. Okay, and then, so this is a new dynamical system. And so if this system has some topological dynamical system, if and only if the induced system is topological dynamical property. So this was, again, very simple proof using this local entropy theory, but the earlier results were like pretty deep techniques by Glassner and Wise, and very complicated proofs, right, done for measure zero systems. And then very recently, this is, he worked, Felipe Ramos Garcia, and he works in more like symbolic dynamics. So we actually connected up locally entropy theory to descriptive set theory. Because there's a couple of different notions in local entropy theory. People think, well, they're different. They don't know how different they are. So using descriptive set theory, we show that these things are very different. So what I'll talk about. So again, my point here is what? That this theory is so powerful that you can apply it to lots of different areas. And what I think might be able to, so once you sort of see the talk, maybe there's a way of exploiting it in linear dynamics. I think I've thought about this a little bit, but haven't really explored it since we've got all these experts in linear dynamics here. Maybe there's a way of carrying it over to linear dynamics. Okay, so let's get started more precisely. A topological dynamical system for me here is a compact metric space. Just a continuous mapping. Okay, measurable dynamical system is I have some set X, I have some sigma algebra. Like if you want, just take it to be whatever space Borel says, some measure t, okay, measure t in a measurable transformation. If you want, you can take mu to be probability measure, which we'll do here, and t is is measurable and measure preserving. Okay, so preimage of measure of t inverse of b is b. Okay, so what's the entropy? So if you go okay, so we have a measurable dynamical system, and take a measurable partition of it. This means you just decompose x into a bunch of finitely many sets, or countably many sets if you want, and then you define h mu of p is negative of mu of p log mu of p. You're like, hey, why is this, right? Why is this defined like this, all right? So this is what I was going to say. If you want to hear more about the Shannon's entropy, I can tell you about the motivation behind it, at least a motivation behind it, okay? So you calculate this quantity, okay? Okay, so this is just h mu of p, some partition. So for example, if your space consists of 2 points, 0 and 1, and your algebra is just all subsets, then this would be just like 1. And your partition is 0 and 1. This is the probability of 0 times log of probability of 0 plus 1 times log of probability of 1 multiplied by negative 1. Okay. So this is again from information theory. This is, if you've got a coin, you're flipping it. What's the best compression you can do? This is the number you get. Okay. And if you've got two measurable partitions, then you just look at the common refinement. I call it P whatever upside down Q. Okay, the common refinement. Okay, so what is the entropy of a measurable dynamical system? So the entropy of T with respect to partition P is given by, okay, so you look at what? Well, you look at P, you look at T inverse, remember P is a partition. Now you look at all those preimage of the partitions and so on up to n minus 1, right? I got to start at 0 to n minus 1. But now you look at all the common refinements, you got a new partitions. And then you compute h mu of that. Okay, so you say, hey, log of each one of those times, it's, take P, take an element of here, this thing, measure of that times log of that minus that, what I defined earlier. And the entropy of T is just a soup over all the partitions. Okay, so when you see this, you're like, holy crap. Okay, if I've got first time you see this, and when I saw this, you're like, okay, I got positive entropy. Now what do I do, right? Like, okay, so so first there's things in there with laws in there which I don't understand. And then it's like, well, for some partition, the soup's positive. Okay, I got that. But then, so I got some partition, right? But now I got this lim_inf. Now keep in mind, this thing is a complicated quantity, okay? Okay, so how do I actually use this that entropy is positive? And that's always that was always the thing here, right? So let's go to topological entropy. Okay, so again, this came later. So you say, okay, I got a topological dynamical system, and now I'm going to have open cover, not a partition, but a cover for that. So absolute value or cardinality of C just denotes the least integer k. So there's a subcover of C with cardinality k, which covers C. So this just means, C might have a lot of duplication, right? To look at the least subcollection, the least cardinality of subcover of C. Okay. So topological entropy of T with respect to this should be not a partition, this should be a cover. Okay, this is a mistake. Is given by, what do you do? Well, okay, so you look at the cover C, T inverse of C, and so on. Now this is and then you look at the common refinement. So this is a cover of the space. Now you look at the minimal subcover of that, take log of that, divide by that. And that's HC of T for this particular cover. And then the entropy is soup over all of the covers. Okay. So again, this definition, you're like, okay, I got something with positive entropy. How do I actually use this? Okay. Or how do I even compute the entropy? Okay, computing entropy is non-trivial. Okay, so the point here, okay, one of the things I like to say is, so in the dynamical behavior, the important part is entropy 0 or positive. So when something has entropy positive, then you have other properties, like you have Lie or chaos and so forth. Okay, so often you're not really that interested in what the entropy is. You're just interested in whether entropy is positive or 0. And so that's what I'm going to be focusing on in this talk. Okay, so let me just do, how am I doing on time? I don't remember, what time did we start?
Well,
10 minutes ago?
more or less, yes. So you have 20 minutes or
20 minutes?
20,
25?
25.
Okay. So let me just give a simple example, right? So just you like, okay, all the abstracts, this concrete stuff. So I'm just going to do what we like to do in linear dynamics, except you're going to simplify it, right? So my space is just going to be 0, 1 to the n, and my map is just going to be the shift, okay? Okay, so it's a clearly continuous map, but it's, in some ways as simple as you can get. So I'm going to prove this, that this thing has positive topological entropy. Okay. So what do I need to do? Well, I need to find some cover. What happened here? I can't go backwards?
Yes, you can.
Oh, got stuck.
Don't press too much.
Oh, yeah. Okay, maybe now. Okay, sorry. Yeah, here we go. Okay, so so I need to compute this quantity for some cover C. So what's my simplest cover? Okay, so my cover would be C would be everything that starts with 0, everything that starts with 1. So these are my, keep in mind I'm working in a very simple system, right? A Cantor set, totally disconnected, I don't have to worry about overlaps, okay, and so on. So I got this system, okay, so what is sigma inverse of C? Well, okay, so what maps to 0? Well, everything which has 0 in, so let's say I start at n starts with 0, if we want. Okay, so n is 0, 1, 2, 3, just to be, okay. So this would be everything which has 1 in the first coordinate. Primitive this. And this would be everything which has 1 in the first coordinate. Okay. Because primitive this, how do I get first position 0? Well, I have to have, the 0th position, I have to do that. Okay, so in general, C minus K of C is what? Everything which is 0 in the kth position, and 1 in K. Okay. So what is this quantity here? C sigma inverse of C. Let's go all the way up to sigma. Not the quantity, this covering. What is this? This is, let's say, up to n minus 1. Okay. So I look at, so for example, forget this. So if I look at the intersection of the, okay, here's a cover and here's the cover. I look at the refinement, what do I get? If I just look at the first one. Well, okay, I have 0, so I just look at all the words of length 2, and then whatever I want, right? So I look at the common refinement of these two. Okay. So I look at this intersect this, that means I have 0, 0. This intersect this with 0, 1. This intersect with this, 1, 0, and so on. Okay. So this thing is just basically set of all, let's say tau like this, such that tau is a word of length n. So do you know what I mean by I take a word and then I can finish it up with whatever I like. So how many objects does this have? Keep in mind, all these are pairwise disjoint. So this cardinality is just 2 to the power. This is 2 to the n, and I compute log of, so what do I do? So hc of t, or sigma in this case, well, I take a lim n, right? So 2 to the n, so I just get a log of 2 to the n divided by n, so that's just log 2. Okay, so I just proved this thing has positive entropy. And you're like, okay, very simple. But I chose my example just right. Okay, I just chose my example. So it's zero dimensional. I don't have to have any overlaps. I chose my mapping extremely simple ways. Everything just works just right. Okay. Now it turns out that the entropy of this system is actually log 2. So you can't, if you take any other partition, when you calculate this HCT, you either get log 2 or less. Okay. Now to prove that, it takes a little bit of work because now you're just saying, okay, but if right now in this talk we're only interested in entropy positive or zero. Okay. So keep this example in mind, a very simple example. Okay, so this definition you already know. Vinicius just talked about them, right? And everybody knows. So, the topological TDS is transitive, means all non-empty open sets. You get that. The mixing, you know, right? Vinicius just talked about that. And weakly mixing means the product is transitive. Okay, so let me give you a mixing example. All right, I just want to give an example of a map which is mixing. So you're like, okay, we already know this. You just take a shift, whatever, linear dynamics, right? But let's look at in this context. I want to look at a particular example. Take those 1/3, 2/3, linear map. Okay. This is mixing because what? Well, okay, so this is my map F from 0, 1 to 0, 1. What does F squared look like? Well, it's just going to do the same thing twice, right? And after the n and so on. So in fact, if you give me any interval, if I take Fn large enough, imagine that interval will be entire space. Okay. So this looks very different. You're like, okay, got a formula. But in some sense, this thing is the same. Okay, not same like. Okay, so I could have done this with 3 symbols. Okay, sort of 2 symbols. So in some sense, it's exactly the same example. Okay, so we're not going to make that precise, but you guys see this?
Yeah.
Okay, so in this case, if I take any basic open set, what's a basic open set? Finite strings and then whatever you want. Well, if I take enough powers, I get the whole space. Okay, what's that shift here? So in some sense, this example is not that different from this one. So this one is mixing also. Okay, so let's move forward. Okay, so the variational principle, the connections between topological dynamical system and measurable dynamical system is this: that if you take a topological dynamical system, okay, let M of t be the set of all probability measures which are t invariant. You remember, it's back to that. And the topological entropy is actually the soup of the measure theoretic entropy. Okay. So one way of defining, if you got a, in context of unusual context of defining.
Probably this should be Borel probability measures.
Yeah, Borel probability measure, sure. Yeah. Oh, yeah. I mean, I'm dealing with, this is all Borel probability. Yeah, the set of all Borel probability measures mu, which are t invariant. Okay. So this is one way of defining. If you want to define entropy, for example, in linear dynamics, one thing you can do is like, hey, look at probability measures on your thing which are invariant. You always know you have one, right? Because 0 is always a fixed point, right? And so you got everything of 0 as probability measures. So in general, you don't even know, right? I mean, a priori, you don't even know if there's at least one invariant measure on it. Okay? So and here, I mean, that takes some work. It's a classical theorem, but okay, you at least have one invariant measure, right? In topological dynamics. In linear dynamics, it's really easy, just And so this is one way of defining topological entropy in linear dynamics. Not sure if it's a good way or not. We can talk about that later. Okay, so this is the variational principle. Okay, so let me go back to the sort of connection between ergodic theory and this other stuff here. So this is something called K-systems. I didn't give a name to this. This is a classical theorem of a variety of people, probably Kolmogorov in there and so on. So So these are very classical theorem, right? So you have a measurable dynamical system. Then the following are equivalent. Each partition P of X, we have that the entropy with respect to that partition is positive. For each two-element partition of P of X, we have that the entropy is positive. Okay. T has what they call complete positive entropy, okay, i.e. each non-trivial factor of T has positive entropy, measure theory says. So what is this trying to get at? So let's say I look at this particular example. I go from 0, 2 to 0, 2. Okay. And here is just the identity. Okay. So if I pick this particular partition, okay, now I'm switching to measure theoretical dynamics here, right? Okay. Well, look, these sets are invariant, okay? So when I do my, look at the decomposition, look at its pre-image, I just get the same thing. So the entropy is 0, okay, with this particular partition. Okay. We know the entropy is positive because I can take a partition here and get it, okay? So the whole idea here is this: if you have a K-system, entropy is positive everywhere, okay? That means no matter what partition you pick, okay, you get positive entropy, measure theoretic entropy. Okay. So in some sense, you could have positive, you could have a system that's positive entropy, then you can just attach something to it, which is really nice, and everything's invariant, and you still have positive entropy, but now you don't know where the entropy kind of lies, right? So if you have a K system, you've got positive entropy everywhere in some intuitive sense. Now all of these conditions imply strong mixing in measure theoretic sense.
This is your result?
No. Oh, no. This is a very classical result.
Very classical.
No, okay. This is definitely not my result. This is probably going back to, I don't know, Kolmogorov and whoever, right? So, yeah. So I'm extremely modest when I state my result. I'll put my name to it, right? If my name's not attached to it, okay. It's not my result, okay? I'm not that modest that I'll state my result without putting my name on it, okay? So these are definitely not, yeah. Okay, so let's go to topological dynamics. So is it clear what the significance of this is? So this says you got entropy positive sort of everywhere in some sense, wherever you look. Okay. The topological dynamical system, it turns out, okay, so the Blanchard defines something called uniform positive entropy, okay, and complete positive entropy to capture the above relation. So uniform positive entropy is what? Well, just like what we had earlier, you take a cover with just two elements, okay? Well, you pick an essential cover, because now keep in mind they're not disjoint, it's a cover, open cover. So you just say what? The closure of neither one is the whole space, okay? Then you say, hey, with respect to this cover, entropy is positive. So no matter how you break it up, you get positive entropy, okay? And then you define something called complete positive entropy, just trying to do the parallel there, but the non-trivial factor have positive entropy. Non-trivial means factors with more than 1 point, okay? So he proved the following, that UPE, uniform positive entropy, implies CPE, UPE implies topological weak mixing, and there are CPE systems which are not UPE. Okay, so this, in measure theoretical dynamics, all these things are the same. Okay, so this is basically UPE, and because you take partition with two elements, positive entropy, CP, all these are equivalent. In topological dynamics, UPE implies CPE, but they're CPE systems are not UPE. Okay, so this is very different. So the whole point here is trying to define K system in topological settings. Okay? So he gave this example. Let me see here. Okay, so I just did something quickly here, right? So he gave this example, and then Felipe Garcia Ramos and his collaborator Barbieri proved that, okay, so you can actually assign a countable ordinal to each CPE system. Okay? And they proved that, well, for every ordinal you can find a CPE system which is so complicated, CPE, but still not UPE. And so when I met him at a meeting first time I met him, he said, oh, you know descriptive set theory? I'm like, yeah. And then so we actually got used descriptive set theory to prove that something is Borel. I mean, this UPE system is Borel, and CPE system is not Borel. And then actually you can even get mixing examples like this. This paper, I mean, it's pretty complicated, or the descriptive set theory is, but it's on the archive. It should be, yeah, it's done. Okay, so that's sort of the descriptive set theory part of the thing that I want to say. Okay, so here's the thing. So this is the main part, sort of one of the main things that I want to talk about. So how do I actually, suppose I have positive entropy, topological entropy. Can I do something besides just say, hey, there exists a cover for this, blah, 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 okay? Because then I just don't know what to do. So if I could make it to look something like the shift, that would be great. Okay, and this is sort of the beautiful theory. This is the local entropy theory. So I'll describe what the theorem is in a second. This is sort of the final result of Karen and Lee. But we need a couple of definitions. Okay? So we have a collection. Okay, the set has positive density here. That's just the lower density that we usually talk about. By positive density, I mean positive lower density here. And I've just got two elements set. Okay, I don't even care open or not or whatever. Okay, and we say IN is an independent set for UV if for all infinite J in I, and for all in here, this is non-empty. You're like, okay, this is a handful, right? So let me just draw a picture. So I have I is some subset of N. I'll list it, I1, I2, up to some I for K. And here I have U and V. So I just look at T minus I1 of V, T minus I1 of U, and same in each coordinate. Okay? This is V. So he says, look, I look at any, okay, so I've got a table like this right here. So he just says, look, I look at any possible strand, one from here, one from here, one from here, one from here, the intersection is non-empty. Okay, so this is kind of, remember kind of like 0-1 shift, it's kind of beginning to look like that. Think about this is 0-1, okay, 0-1, okay? Except you're not going through, you know, integer index, you're going through I1 through I. Okay. So this is what it means for I to be an independent set for UV. Keep in mind, we're already in TDS because we already have a mapping. And this is written in the formal way. Okay, so this is a picture because I usually do some iPad. So here's the theorem. Okay, so for topological dynamical system, we say X1, X2 is an independence pair, or IE pair, independence entropy pair, or IE pair, if for every pair of open sets A1 and A2 containing one and the other, there exists an independent set of A1, A2 with positive density. Okay. The set of IE pairs is denoted by EXT. So what does this say? Okay. So it says, look, X1, X2 is an IE pair. That means no matter what open set I pick around here and open set around here, depending on the open sets, I can set with positive density, such that if I take any finite set out of this intersection here is non-empty. Okay? So the theorem, this is the beautiful theorem, is that take a topological dynamical system, and keep in mind, if X1 is X2, you always have the intersection is non-empty, right? Because the same, you can take the intersection, right? So that the point here is, if you're a topological dynamical system, it has positive entropy if and only if there exists an IE pair with X1 not equal to X not equal to Y. And XT has a UPE if and only if every pair is IE pair. Okay, so basically, so what? Okay, so we're not worried about the small sequence relations because this is all the descriptive set theory part. So basically, what this says is this: if I have a set with positive entropy, I can find 2 points. Okay, so let's actually draw a picture here. Okay. Okay, X, comma Y is an IE pair. Okay, so you give me an open set U and V containing it. I'm assuming there's different. Okay. So based on this, I can find a set, what did I call it? Independent set I didn't give it a name. Okay, so you got some set I with positive density. Okay, such that, so I look at P inverse of U here, P inverse I inverse of B here for all i's in here. Okay, right. And then, so keep in mind, these are disjoint, all these things are disjoint. So this is beginning to look like, kind of like 0-1 example, shifts, okay? So it says now, okay, you're not going to require all possible infinite things to be non-empty, because then if you get technically, because you're working with open sets and not closed, and you get complicated. So you just say for any finite set, any finite collection here, the intersection, like I told you here, is non-empty. Okay? So basically, in some sense, it's just, but here, I is not all of the integer. I is not the whole thing, but some sets with positive density. So in some sense, it says, hey, look, if you got positive entropy, it contains something like the shifts example that I just described. Okay, in some sense. And so the beautiful thing about this, so if I have positive entropy, I've got these 2 points, okay? So I've got something actually that I can hold on to, and now I look, I got to start with positive density, so I'm pulling things out of number theory, or densities, and then these intersections are non-empty, okay? So this is an extremely useful result, okay? So let me, so this is the thing that I, when I first saw it, I'm like, wow, and then I'm able to exploit it 3 times very successfully. And so maybe there's another 4 or 9, right, okay. So a CPE example, all right, so we don't have much time, right? How much time, 5 minutes maybe?
Yeah,
maybe more or less. Okay, so let me actually just skip this here. So what I've been able to do, okay, so let me tell you quickly the example, the one line of things that I want to talk about. Okay, so continuum is like compact connected metric space. Okay, so forget about it. There's lots of definitions. It takes a while to digest. Okay, so the idea here is this. Okay, so let me just say this in 5 minutes. So what was done before was this. You take interval 0-1, you could do there. You got some mapping. Okay. It's got positive entropy. Topological entropy is positive. Okay. So what they were able to show, this was like back in the 80s, that if you look at the inverse limit space of this interval with this mapping as a bonding map, the structure of that is very complicated. It contains something called indecomposable continuum. Okay. So but they couldn't do it for other things. Why not? Well, because the way they would do it, the way they did it is like, hey, if you got positive entropy, on interval, that means you have a periodic point which is not power of 2. So if you take some power of it, you got a periodic point of odd order, and then they use that to actually get this complicated structure. Okay. But then they just did, but when you go to a circle or other shape, you just don't have that anymore. The Sharkowski's theorem doesn't work there. Okay. So what we were able to do, so I'll just go quick through the slides here. Okay. So here, I guess give you this was like another 30-minute lecture, right? But so the theorems were. Okay, so this was the theorem that I was talking about. So if you have a dynamical system with positive entropy, the inverse limit space contains something really complicated, which is compact and okay. And then other people had shown that if you have a homeomorphism with positive entropy, then again the domain space has got to be really complicated. Right? And then they had shown that if you've got a graph with positive entropy, then the inverse limit space contains something complicated. Okay, so it's still all of this. So this result used Mizarevich and Lieber result about Sharkowski type theorems on graphs, because you have theorems like that on graphs. Okay. So what we were able to do, okay, again, more with the definitions here. Okay, so I'll give the result. So that's it immodestly when I state my result. So if you have a continuum, which is what's called graph-like, so much more, it could be a graph, but much more general than that. And if you have positive entropy, okay, then the inverse limit space contains something really complicated called indecomposable continuum. Okay? And so in particular, if it's a homeomorphism, then the domain has to be complicated. You can't get a homeomorphism with positive entropy in this setting. Okay? So the whole idea here was this. is that using this IE pair, okay? So we have this kind of dynamic, the IE, the independence set, and then using some topological structure, we were able to do things people couldn't do before because we know we can exploit the local entropy, which people didn't know how to do before because the theorem just didn't exist. And so we did that in a couple of different situations. Yes, here's another theorem of that type. You have a homeomorphism with uniform positive entropy, and not only does it contain something complicated, but it actually itself is something complicated. And I think this is where I'll quit.
For the next talk, are there any questions or comments?
I didn't give any details probably to ask questions.
No, but the pictures are very
yeah.
nice. So, comments, questions? Yes, I think you mentioned before, I mean, this relation between the mesotheoretical entropy and the topological one, because, I mean, yes, I mean, the problem when you are not in compact spaces, I mean,
right,
is how to define also the right, let's say, the right topological entropy, isn't it? So.
Right. So, I mean, mesotheoretic entropy you can define because you don't need.
Yeah, you don't need any.
Because you take probability measure and you invariant, and then you do any decomposition and you do that. So I mean, this could be a candidate, but on the other hand, is it a good? So is it a good candidate? It's not clear because you have to explore it some and then decide like, hey, I mean, is it a property that you want?
You have to know how are the measures, the probability measures on this space.
So for example, you would have to know, okay, what are the interesting invariant measures? The only one is just trivial, then you're not getting really any information out, right? Yeah. So there are lots of interesting questions here, I think. Yeah.
And this variational principle is for compact.
Right.
Yeah, but okay. If you want to define it, but for non-compact, maybe this is one.
Because the thing is, you need invariant probability measures, right? So in general, like, okay, if you don't have that, what is that? Okay, then it doesn't make it. It doesn't work. But in linear setting is great because you at least got the trivial invariant probability measure. Measure of 0 is 1 and everything else is 0, right? So you always have that, but okay, fine. But then is that like that's still not so formally you can define it, but it's not clear if that's a good definition or not. Yeah. Because so I started looking at this with Hedges at some point, but like, okay, so just forget everything else. Just look at the invariant probability measures on for some nice operator, right? Like shift operators, right? And so you can get some results on it, but I mean, so even for just shift after, just 2 times something, right? So you expect that to have, you want positive entropy, like 2 times the shift, because it's frequently hypercyclic, blah 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 blah, right? So you want that to have positive entropy. I would think, okay. So first, if you were to take this as a definition, you just need to say, hey, what are the invariant probability measures? Okay, and then for some of them, can I get positive entropy?
Yeah. Or maybe you can restrict to a class like Gaussian. In the linear dynamics, Gaussian measures are very well studied by the French team. I mean,
right, but you want them to be invariant, right?
Yeah, of course, yes, of course. Gaussian and invariant, and under some properties of the operator, these things happen and so on, and
yeah. So I mean, so for example, just the fact that 2 times the shift, right? So okay, I mean, we would agree that you wanted to have positive entropy, right? We may not agree on what that number might be. Okay? Should it be infinite? Should it be whatever? But
probably Antoni knows because I mean, you were. I mean, when do invariant? I mean, conditions for the operators are that there are invariant Gaussian measures.
Gaussian measures are more in Hilbert spaces.
For Hilbert spaces,
there is a lot of theory about when you can exchange an invariant measure with a Gaussian measure with the same covariance operator and all these things.
Yeah.
But for instance, if you are in a reflexive Banach space,
this is Bayard-Griveau result, right?
Yeah. Well,
no, in the Matheron-Griveau result.
Yeah. But if you are in a reflexive
Right.
Banach space, then you can construct invariant measures easily.
Right. Which have some nice properties.
Yeah.
Right. Exactly the Matheron-Gribov result.
Yeah. Okay.
Because of the weak
from
star.
that result, we had the other.
Because of the weak star topology.
Yes, because
Right.
you have a lot of compact sets.
Right.
Then you can do things.
Right.
Because
right.
if it's
But
reflexive,
for
the
these
unit-
operators, you have at the end the operators in which you can have an invariant measure of full support, or maybe just invariant measures, not assuming full support, full support thing, are those which have strong recurrence
Right.
properties.
And so for like 2 times shift would fit
Yes,
into this.
yes,
right?
for sure.
So here you have lots 2 times shift, you have lots of invariant measures.
Yeah.
Right. Because just from the Gribov, Matheron-Gribov
Yeah.
result. Yeah.
So for this class of operators, maybe you can define the
Yeah, exactly.
measure entropy, right? But I don't know.
Right. And then define the topological as this. I don't know what the actual number would be for the actual topological. You take the soup over all the measures, right? I don't know. That would be kind of
Is the supremum
attained.
attained in the ergodic measure?
No, sometimes. Yeah, that's like no.
I mean, the ergodicity doesn't play. I mean,
Right.
you always have an ergodic, at least. an
Right.
ergodic.
So there are cases where it's attained, there are cases where it's not
Okay,
attained.
okay.
Right. So it depends on the
I don't
situation.
know.
Yeah. But exactly, good question. Yeah. So for example, right? I don't know, just detailed study of just 2 times shift or whatever, lambda times shift. Okay. So exactly what happened, that would be kind of interesting because we already have stuff like Matheron-Gribov's result. Yeah. So you already know something non-trivial exists. It's not just like yeah.
Okay.
Okay. Thank you. Yeah.
More comments? Thank you again.
Sure. Thank you.
Time for lunch.
Yeah.